Geology. Module 17, Ore Geology. 1. Introduction. Most of the modern conveniences in our daily life are reliant on the mineral deposits present in the Mother Earth. The demand for the natural mineral resource has been increased to many folds with the industrial growth as well as increase in human population. The knowledge and understanding of the mode of occurrence, genesis and distribution of the mineral deposits are important for the sustainable development of these mineral resources. Ore geology is the field which covers major aspects pertaining to the description, understanding and genesis of the ore deposits. Broadly, ore geology is the study of the formation and extraction of the minerals of economic importance. Since the mineral resource development has huge impact on the socio-economic and environmental scene of any country, this discipline is equally important for the students and scientists of environmental sciences also. The mineral deposits or deposits form when a mineral, element or group of minerals, elements is sufficiently concentrated in any part of the Earth's crust so that can be extracted with profit. It is broadly classified into two categories as A. Metallic mineral deposit or deposits from which one or more metals can be extracted with profit, e.g. deposit of gold, iron, lead, zinc, copper, etc. B. Industrial mineral deposit or non-metallic mineral deposits from which mineral or minerals, which can itself be used for one or more industrial purposes and are useful because of their unique physical or chemical properties, e.g. deposits of barite, gypsum, mica, fluorite, talc, etc. In this module we shall be trying to understand the processes which are responsible for the formation of the ore deposits. 2. Ore minerals and GANGUE minerals. Any naturally occurring material from which a mineral or group of minerals of economic importance can be extracted with profit is defined as ore. It normally consists of ore minerals and gangue minerals. The ore minerals are those minerals, in ore deposits, which are of the economic interest, e.g. chalcopyrite, pyrite, galena, sphalerite, magnetite, chromite, etc. All the other minerals present in the ore which are not of any economic interest, little or no value, are called as gangue minerals. In the metallic deposits sometimes associated accessory sulfide and oxide minerals, e.g. arsenopyrite in gold deposit, chalcopyrite and pyrite in PBZN deposits, etc., are also called as ore minerals though they constitute part of uneconomic, unutilized gangue minerals. 4. Environmental geology. Out of more than 3,800 minerals identified till date, only a few make up the bulk of the rocks of the Earth's crust, as the common rock-forming minerals. Further, much lesser number of minerals, called as ore minerals, is available to form most of the economically viable ore deposits of the world. The common ore minerals can be grouped into 5 categories based on their chemical composition as native elements, sulfide ores, oxide ores, carbonate ores and halides, Table 1. Very few metals are mined in their native form, i.e. containing 100% of that metal. Copper, gold and platinum are the commonest metals present in native form. Most of the ore minerals are present in form of sulfides and oxides, however some carbonate and phosphate ore forms also not uncommon. Silicates, which are the most important form for the rock-forming minerals, are less common form for ore minerals. Table 1. Classification of ore minerals. Chemical class of ore minerals. Important ores. Native elements: native gold, O, native silver, Ag, native platinum, point. Sulfide ores: chalcopyrite, Cus2, chalcocite, Cu2s, bornite, Cu5Fes4, cobalite, Cus, galena, PBS, sphalerite, ZNS, pyrrhotite, Fe1xs, pyrite, Fes2, pentlandite, Fe, Ni9s8, millerite, Nis, cinnabar, HGS, cobaltite, Coas, molybdenite, Mos2, realgar, As, orpiment, As2s3, stibnite, Sb2s3, argentite, Ag2s. Sulfosalts, tetrahedrite, Cu, Ag12Sb4s13, tennantite, Cu, Ag12s4s13. Oxide ores: cuprite, Cu2O, hematite, Fe2O3, ilmenite, Faseo3, magnetite, Fe3O4, chromite, Fecar2O4, pyrolus. Five. 3. Nature and morphology of ore deposits. As we understand by now that an ore body is a mixture of valuable minerals and waste rock. Each ore body, which has a definite size and shape, is a mass that contains enough valuable mineral to be mined and processed at profit. The field observations of the ore bodies, like their mode of occurrence and relationship with the host rocks, their relation with the regional stratigraphy and structures, give the first-hand information about their origin. The pattern of distribution of ore minerals in a host rocks and the contact of the ore body with the immediate host rock may either be sharp or gradational or diffused or invisible to naked eyes. The contact of ore body and host rock is called sharp when there is an abrupt change in the critical physical and chemical parameters of the system, e.g. presence of discordant ore vein or concordant ore layers within any rock. The gradational or diffused contact signifies a gradual change in the mineralization fronts, while the invisible contact is defined by the assay value of the ore element only and the ore body does not have any physical identity. Shapes of ore bodies can be classified as A. Discordant, i.e. vein type deposits. B. Concordant, i.e. stratiform ore deposits. 3.1 Discordant ore bodies. The discordant ore bodies have a cross-cutting relationship with lithological boundaries and or the internal structures of the host rocks. They may be regularly shaped or irregularly shaped bodies. Table -2. The regularly shaped bodies may further be divided into tabular or tubular type of bodies. A. Tabular ore bodies. The tabular ore bodies are extensive in 2 dimensions and less developed in their 3rd dimension. Veins and lodes fall in this category. The veins are generally formed either by the movement of ore fluids through the cavities, weak planes, and infilling the pre-existing open spaces in the host rocks, or by replacing the masses along a permeable feature. They are often as we understand by now that an ore body is a mixture of valuable minerals and waste rock. Each ore body, which has a definite size and shape, is a mass that contains enough valuable mineral to be mined and processed at profit. The field observations of the ore bodies, like their mode of occurrence and relationship with the host rocks, their relation with the regional stratigraphy and structures, give the first-hand information about their origin. The pattern of distribution of ore minerals in a host rocks and the contact of the ore body with the immediate host rock may either be sharp or gradational or diffused or invisible to naked eyes. The contact of ore body and host rock is called sharp when there is an abrupt change in the critical physical and chemical parameters of the system, e.g. presence of discordant ore vein or concordant ore layers within any rock. The gradational or diffused contact signifies a gradual change in the mineralization fronts, while the invisible contact is defined by the assay value of the ore element only and the ore body does not have any physical identity. Shapes of ore bodies can be classified as A. Discordant, i.e. vein type deposits, B. Concordant, i.e. stratiform ore deposits. 3.1 Discordant ore bodies. The discordant ore bodies has a cross-cutting relationship with lithological boundaries and or the internal structures of the host rocks. They may be regularly shaped or irregularly shaped bodies, table -2. The regularly shaped bodies may further be divided into tabular or tubular type of bodies. A. Tabular ore bodies. The tabular ore bodies are extensive in 2 dimensions and less developed in their 3rd dimension. Veins and lodes fall in this category. The veins are generally formed either by the movement of ore fluids through the cavities, weak planes, and infilling the pre-existing open spaces in the host rocks, or by replacing the masses along a permeable feature. They are often inclined. However, horizontal veins are also not uncommon. They generally occupy fault, fractures, and joints in the rock sequences. Pinching and swelling feature of the veins is also frequently observed. Fig 1. This may be due to the differential competencies of the rocks through which the ore fluids passed. Shear zones act as common important locations of vein deposits, for example the Singbum shear zone. When many parallel veins with high density occur in a deposit, they are known as sheeted veins. 6. Environmental geology. B. Tubular ore bodies. The tubular ore bodies have limited extension in 2 dimensions but are extensive in the 3rd. The horizontal or subhorizontal tubular bodies with roughly circular cross-section are called as mantos. When the tubular bodies have vertical or subvertical extensions, such ore bodies are known as pipes or chimneys. Branching of mantos and pipes are common. Both the mantos and pipes often occur together. Pipes may be of various types and origins. Irregularly shaped ore bodies are of 2 types, namely disseminated type and irregular replacement type. A. Disseminated type ore body. The ore minerals are disseminated throughout the host rocks like any other accessory mineral. A good example of is the diamond and kimberlite and copper deposits of Melanchthon. Many times the ores are concentrated as dissemination or pockets into group of closed-spaced veinlets with sharp walls which are crisscrossing each other and occurring in a bigger zone, popularly known as stockworks. These types of ore bodies are often irregular in form and may cut across the lithological, geological boundaries. Many of the world's copper and molybdenum deposits forms disseminated type of deposits apart from some tin, gold. B. Replacement type of deposit. The ore bodies formed due to the replacement of the pre-existing rocks due to metasomatism and thermal metamorphism. These deposits are extremely irregular in shape. Belka Pahar Wollastonite deposit in Rajasthan is an example of such type. Fayre copper or tin skarns are common replacement type of deposits. Some horizontal to subhorizontal of ore bodies lie in carbonate host rocks beneath an impervious cover formed due to branching out of the veins. Fig 2. Such features are called as flats. 3.2 Concordant ore bodies. Concordant ore bodies are normally present as layers parallel to the beddings. Sedimentary host rocks. Concordant ore bodies in sediments are very important producers of many different metals, being particularly important for base metals and iron, and are of course concordant with the bedding or other structural features in the host rocks. They may or may not be an integral part of the stratigraphical sequence. Usually these ore bodies show a considerable development in 2 dimensions. Such bodies can be present in sedimentary or igneous host rocks. Volcanic hosted massive sulfides and stratiform chromite deposits are some of the examples present in the igneous rocks. 7. Environmental geology. Figure 1 vein occupying normal fault and exhibiting pinch and swell structure and giving rise to ribbon ore shoots. Figure 1 vein occupying normal fault and exhibiting pinch and swell structure and giving rise to ribbon ore shoots. Source: Fig 2.2 on page 27 of the book by Evans, 1993. Figure 2, PBZN body in a faulted anticline at Umushlag, Russia. Source: Fig 2.12 on page 33 of book by Evans, 1993. 4. Classification of ore deposits. The geological literature has many schemes for classifying the mineral deposit based upon the commodity, copper deposits, iron deposits, etc., morphology, environment and origin. The older classification schemes were mostly based on the mode of origins of the ore deposits. However, with the development in the subjects they became obsolete. A comprehensive review of various classification schemes can be found in Wolf, 1981. The classification schemes based on the origin of ore deposits, however, are widely used. However, in recent years the classification schemes are modified to take account of environmental rock associations. Lindgren's classification was one of the very popular classification schemes for the ore deposits. Table 2. He tried to place the physical and chemical processes with temperature and pressure zones. Table 2. Lindgren classification. 8. Environmental geology. 9. Environmental geology. 10. Environmental geology. 5. Process of formation of ore deposits. 5. Process of formation of ore deposits. All the common ore-forming elements, e.g. Cr, Ni, Cu, Pb, Zn, O, Ag, W, Sn, Fe, Al etc. are present in the magma and other rocks in varying amount. Favorable conditions, like extraction of the elements from source region magma, rocks and water, their transport in a fluid medium from source region to the site of deposition and deposition of elements at appropriate place, is required, which leads to a much higher concentration of one or more elements in a limited portion of the earth to form mineral deposits. Various theories of ore formations explain 4 questions about the mineral deposits. In general, the giant deposits are formed when the source of metal is large and the transport mechanism of transport of ore fluid is efficient and proper physico-chemical conditions for deposition is available. It can be summarized in 3, W, S and 1, H, i.e. when the deposit is formed, where the deposit can form, why the deposit was formed, and how the deposit was formed. The deposits are classified as syngenetic and epigenetic depending upon the timing of the formation of the deposit with respect to the surrounding host rocks. The syngenetic deposits are those deposits which are formed at the same time as the host rock body. A good example of the syngenetic deposits is the banded iron formations. The epigenetic deposits are those ore deposits which are formed at later time after the host rocks has formed. Gold-bearing veins cutting across a granitic pluton is an example of the epigenetic deposit. Further, the theories regarding ore-forming processes can be broadly classified into 2 categories as endogenic processes. These are the internal earth processes responsible for the formation of ore deposit. The endogenic processes of deposit formation include magmatic segregation processes, magmatic injection process and hydrothermal processes. B. Exogenic processes, processes which operates over the surface and are responsible for the formation of ore deposits. These processes include sedimentary precipitation, residual concentration processes, supergene enrichment process and volcanic exhalative processes. In some cases, more than one process are responsible for the formation of ore deposit. For example, sulfide accumulation is a chemical sediment from metal-bearing hydrothermal fluid, endogenic process, discharged on the sea floor, exogenic process, to form a exhalative deposit. 5.1 Endogenic ore-forming processes. 11. Environmental geology. The internal forces inside the earth are responsible for such ore-forming processes. The ore deposits formed by the endogenic processes include orthomagmatic chromite deposit, magmatic Ni-Cu sulfide deposit, gem-bearing pegamatite deposit, porphyry copper deposits, skarns deposit, cavity-filling hydrothermal deposits, replacement deposits, etc. These processes can broadly be classified into 3 main categories as A. Magmatic processes, B. Hydrothermal processes and C. Metamorphic processes. These processes are briefly discussed here. 5.1.1 Magmatic processes for ore formation. A wide range of the ore deposits are hosted by mafic and felsic igneous rocks. Studies reveal that many of such deposits are directly crystallized from the magma. The examples range from crystallization of diamond in kimberlite to early crystallization of chromite ore from the mafic magma by crystal fractionation to late crystallization of tin from felsic magma. In order to form the ore deposits, the magmas tend to get enriched in the metal concentration from the source area from which they are generated. Magmatic segregation in mafic magmas results in economic concentrations of crossing, T, Fe, and B through orthomagmatic processes, i.e. concentration of ore minerals as a direct consequences of magmatic crystallization. Sn, W, U, Th, Li, B, Cs, Mo etc. are the elements which are generally concentrated in the felsic magmas which crystallize to form granites. Late magmatic processes give rise to the volatile, dominantly aqueous and carbonic, fluid phase which has a dominant role in the formation of ore deposits, magmatic hydrothermal processes. The ore constituents present in magma may be concentrated further during the course of crystallization through various processes. The magmatic ore forming processes can be divided into 2 main categories as A. Magmatic crystallization and B. Magmatic segregation. A. Magmatic crystallization. The ordinary processes of crystallization during cooling of magma by which certain important minerals crystallized along with the main plutonic and volcanic igneous rock. The best example is the diamond in kimberlite or sapphire in pegmatite. B. Magmatic segregation. The terms magmatic segregation is the process in which the ore deposits are formed by the direct crystallization from magma through various mechanisms. 2 important mechanisms through which the ore minerals get segregated to form ore deposits are fractional crystallization and liquid immiscibility and are described below. I. Fractional crystallization. In this process the ore minerals crystallize directly from magma and get segregated to form deposit by any of the igneous processes like gravitative crystal settling, flowage differentiation, filter pressing or dilation. The early formed crystals are thus prevented to get equilibrated with the melt from which they form. Whatever the formative processes may be, their products are the rocks and called. 12. Environmental geology. Cumulates. The cumulates thus formed often display rhythmic layering. The crystal settling, convective fluid flow, and diffusion-related chemical segregation across density stratified layers seem to be the logical way to explain the characteristically subhorizontal, well-ordered layering evident in most layered mafic intrusions present in different parts of the world. The excellent example of this type of magmatic deposit is stratiform chromite deposit of Bushveld igneous complex in South Africa, Figure 3. The detailed explanation of the process for the formation of monomineralic chromite seams is given by Irvine, 1997. Lack of efficient segregation from the silicate minerals would normally result in low-grade disseminated mineralization. Magmatic segregation deposits may also form by the crystallization of residual magmas by squeezing out through filter pressing process and forming a magmatic injection type of deposits. The Fe T oxide deposits associated with anorthositic gabbro are believed to have formed by such processes, Fig 4. Figure 3. Chromite black and anorthosite light gray in Bushveld igneous complex. Source. 13. Environmental geology. Figure 4. Diagrammatic representation of the formation of Fe-T oxide deposits by residual liquid segregation and residual liquid injection. 1. Early stage of crystallization of a basic magma, after formation of chilled zone. B. 2. Layer of sunken early formed ferromagnesian crystals, C. Resting over the chilled zone, with mesh of later crystals above, whose interstices are occupied by residual magma enriched in ore oxides. 3. Mobile, oxide-rich residual liquid draining down to layer D and floating up later silicate crystals. 4. Formation of a concurrent oxide ore body in which few late silicate crystals are trapped. 3a. 4a. Mobile enriched gravitative accumulation. D. Squeezed out or decanted to form late magmatic injections. After Bateman, 1951. Source. Fig 2.14 on page 32 of the book by K.C. Mishra. E. Liquid immiscibility. The phenomenon of separation of a cooling magma into two or more coexisting liquid fractions, phases, is known as liquid immiscibility. 3 cases of liquid immiscibility under geologically reasonable conditions have been demonstrated by experiments. These are a separation of Fe-rich theolitic magmas into two liquids, one rich in CO2 felsic, another rich in Fe mafic, silicate oxide immiscibility. B. Spiliting of CO2-rich alkali magma into CO2-rich melt and silicate-rich melt. And C. Segregation of sulfide melt and Haven silicate melts from a sulfide-saturated mafic, ultramafic magma, silicate sulfide immiscibility. Demonstrated. Silicate sulfide immiscibility in mafic magmas is widely accepted as a common feature of magma crystallization. As the magma cools, sulfides droplets separate out and coalesce to form globules. Due to higher density, these sulfide globules sink through the silicate magma and accumulate at bottom of the intrusion or lava flow. Figure 5. Iron sulfide is the commonest sulfides formed by this process in basic and ultra-basic rocks. But nickel, copper and platinum also occur. Comatite-hosted Kambalda Niku deposit, Australia and Sudbury Niku deposit, Canada is the typical examples of this type of deposit. The settling out of the heavier sulfides results in the peculiar net textured ores often found in these deposits. The titanium deposits associated with anorthosite are also considered to be formed by the oxide silicate immiscibility process. 14. Environmental geology. Fig 5. Batch segregation of sulfide phase from a cooling magma after Naldrit et al. 1984. Source. Fig 2.5 on page 15 of book by K.C. Mishra. 5.1.2 Hydrothermal processes. There are enough examples to support the view that the majority of ore deposits around the world are formed either directly from precipitation from the hot, aqueous solutions circulating through the Earth's crust, or have been significantly modified to varying degree by such fluids. These fluids are known as hydrothermal fluids. A hydrothermal fluid can be defined as a hot 50 to greater than 500 C aqueous solution, containing solutes that are commonly precipitated as the solution changes its properties in space and time. Per Arjno, 2009. Different ore-forming processes are involved in the precipitation of ore constituents from the hydrothermal fluids. These can be applied at varying pressures and temperatures that range from those applicable at shallow crustal levels to those deep in the lithosphere. Many different types of fluids are involved in hydrothermal ore-forming processes. The most primitive or juvenile fluid originates from cooling magma and are popularly called as magmatic hydrothermal fluids. Epithermal gold deposit, vein-type SNW deposits, deposits associated with pegmatites and porphyry Kuo deposits etc. are some of the examples of the ore deposits formed by the magmatic hydrothermal fluids. The other types of hydrothermal fluids include those formed from the expulsion of pore fluids during compaction of sediment, from meteoric waters, from the circulation of seawater through ocean floor and from metamorphic dehydration reactions. Lindgren, 1933 classified the hydrothermal mineral deposits into three major groups, based on their PT conditions of deposition and depth of emplacement, as 1. Hypothermal deposits, deposits formed at high temperature, 305,000 C, very high pressure and great depths. 2. Mesothermal deposits, deposits formed at moderate temperature, 203,000 C, high pressure and intermediate depth. And 3. Epithermal deposits, deposits formed at low temperature, 52,000 C, moderate pressure and at shallow depth. Later workers added telethermal deposits. 15. Environmental geology. Formed at low temperature pressure end of the spectrum, Graydon, 1933, and xenothermal deposit for the deposits formed at shallow depth but with high temperature, Buddington, 1935. In modern literature, however, these terms are used only in qualitative sense as the fluid inclusion research on hydrothermal deposits do not confirm such discrete PT regimes. Hydrothermal deposits encompasses a large spectrum of deposit types. In order to explain the formation of a hydrothermal deposit, one need to understand the source of fluid, source or sources of metal or constituents, transport mechanism for the ore-rich hydrothermal fluid from source to place of deposition and favorable conditions, environment for precipitation of ore constituents to form a deposit. The potential source for the ore constituents are the magma and the crustal rocks along which the fluid passes. Vein-type tungsten deposit of China, tungsten deposit of Ghana, India, Kupferschiefer copper deposit of Germany, white pine copper deposit, USA, Mississippi Valley type PBZN deposit, epithermal OAG deposits, Kohler gold deposits India etc. are some of the examples of hydrothermal deposits. 5.1.3 Metamorphic processes. Metamorphic processes are equally important process which leads to form either a new mineral deposit or modify the existing mineral deposit. These processes may include deposits formed by the recrystallization, reconstitution and mobilization of the ore constituents during and as a direct consequences of the metamorphism. The metamorphic mobilization means the movement and concentration of the ore constituents, already present in the pre-existing rock, as a consequence of the metamorphism. All the processes of regional metamorphism, or contact metamorphism may give rise to the mineral deposits. The examples of the mineral deposits due to metamorphic processes include graphite, asbestos, kyanite sillimanite deposits etc. The Mn oxide Indian gondite ores deposit of Goldangri, MP in India is one of the typical deposit developed during regional metamorphism. The metamorphism of the pre-existing mineral deposit may also remobilize the ore constituents further to enrich the pre-existing deposits, and such deposits are known as metamorphosed deposits. The mobilization or remobilization may be chemical, fluid state transport through wet diffusion, solution and melting, or mechanical, solid state transfer through plastic and cataclastic flow, diffusion or grain boundary sliding, or the combination of both. Graphite deposit of Sri Lanka and Rossing uranium deposit, Nambia are some of the examples of metamorphic deposit. The Rampura Gucha PBZN deposit of Rajasthan, India also show evidences of the metamorphosed ores. 5.2 Exogenic ore forming processes. These are the processes which are dominant on or near surface. Under favorable conditions, the normal sedimentary processes may selectively enrich the sediments and/or sedimentary rocks in metals, elements of economic use. They may include the normal mechanical and chemical sedimentary processes or the chemical weathering processes. The normal sedimentary processes may form the placer deposits through clastic accumulation or form the chemical, biochemical precipitation of economically important minerals like 16. Environmental geology. Gypsum, halite, phosphorite, iron ores etc. The chemical weathering may include the residual concentration and supergene enrichment processes. Another important type of exogenic process is the exhalative processes, which are basically surface expression of the activity of hydrothermal solutions. 5.2.1 Sedimentary processes. Broadly speaking, sedimentary processes can be divided into two large groups: clastic sedimentary processes, clastic pyroclastic deposits, and chemical biochemical processes, non-clastic deposits including the evaporites. A. Placer deposits. The mechanical accumulation of the economically important inert and heavy minerals gives rise to placer deposits. Usually the weathering of the appropriate source rock releases the resistant minerals and is transported through the related medium, mostly moving water. During the transportation, a natural gravity separation takes place and concentration and deposition of economically important ore constituents at suitable sites take place to give rise placer deposits. Such placer minerals normally possess high density, chemical resistance to weathering and mechanical durability. Placer deposits of diamond, gemstones, ruby, sapphire, garnet etc. native element O, and PGE cassiterite, wolframite, ilmenite, chromite, columbite, tantalite, magnetite, monazite, xenotime and zircon are common. Modern placer deposits have wider geographical distribution as they are formed by the normal surfacial processes. The majority of placer deposits are small and low grade. Mostly the placer deposits have formed throughout the geologic time, but most of them are of recent and tertiary age. Some Precambrian palaeoplacers like Witwatersrand gold deposits, South Africa, uranium in Canada are yielding good production. Based on the geological environment in which they are formed, the placer deposits are classified as residual, formed near the source, alluvial, formed upon the hill slopes near the source, colluvial, accumulation at the base of a cliff or slope, alluvial, also called as stream or fluvial placers, as the economic minerals are transported and accumulated by streams, beach, deposited on ocean. Based on the geological environment in which they are formed, the placer deposits are classified as residual, formed near the source, alluvial, formed upon the hill slopes near the source, colluvial, accumulation at the base of a cliff or slope, alluvial, also called as stream or fluvial placers. Based on the geological environment in which they are formed, the placer deposits are classified as residual, formed near the source, alluvial, formed upon the hill slopes near the source, colluvial, accumulation at the base of a cliff or slope, alluvial, also called as stream or fluvial placers, as the economic minerals are transported and accumulated by streams, beach, deposited on ocean, beach, etc. The alluvial and beach placers are the most important type. The alluvial placers deposits of gold, uranium, diamond, platinum and tin are commonly present in different parts of the world. In India, because of the placer gold contents in the stream sediments, a river is named as Swarnreka, line of gold, in Singhbhum area. The beach placers are formed either by carrying of ore constituents bearing material by the stream into ocean or by winnowing action of waves and currents along the shorelines where the source of the economic minerals are present. Monazite, ilmenite, rutile, garnet, gemstones etc. are some of the important minerals in the beach placer deposits. Though the fluid dynamic processes involved in placer formation are invariably very complex, the formation of placer deposits is essentially a process of sorting light from heavy. 17. Environmental geology. Minerals during sedimentation. The mechanical concentration of economic minerals normally controlled by gravity, shape and size of particles is the most common process in any type of the placer deposits. Fall in the velocity, hydraulic equivalence, bed configuration, grain size and density etc. are some of the factors which are responsible for the concentration of the economic minerals in such types of deposits. Occurrences of the diamond placers of the Orange River and the western coastline of southern Africa, the cassiterite SN placers of the west coast of Peninsula Malaysia, and the beach-related, black sand, placers Th of Western Australia, South Africa, and India. Late Archean Witwatersrand and Huronian basins, O and U, in South Africa and Canada respectively are some of the important high-yield palaeoplacer deposits. The origin of these ores is, however, controversial. B. Chemical precipitation. Chemical precipitation of the sediments refers to the process responsible for the precipitation of dissolved components from solution, seawater or brine. This is in contrast to the above-discussed mechanical processes of sedimentation to form placer deposit. The examples of the chemical sedimentation and compaction include limestone and dolomite, chert, evaporites, ironstones and banded iron formations, phosphorites etc. Some of these non-clastic rocks like limestone, evaporites, phosphorites etc. are of economic value due to their special properties. Some of the ore minerals get precipitated along with other chemical sediments due to favorable pH conditions of depositional environment. The majority of the world's Fe, Mn, and phosphate resources are the products of chemical sedimentation and are hosted in chemical sediments. The chemical processes by which ore concentrations form are complex and controlled by parameters such as pH, as well as climate, paleolatitude, and biological atmospheric evolution. Most chemical sediments form in marine or marginal marine environments. The continental shelves, together with intradedal and lagoonal settings, represent the geological settings where chemical sediments and associated deposits are generally located. Bog iron deposits, ironstones and banded iron formation are some of the important source of Fe and are formed by chemical sedimentation. It is well known that the iron occurs in two, namely Fe in surface waters and Fe. Principal concentration mechanism for iron in situ deposits relate to the concentration of iron, when aqueous solutions containing Fe, in a relatively reduced environment, are oxidized, with the subsequent formation and precipitation of Fe. The bog iron ores are principally formed in lakes and swamps. The deposits comprise of the concentration of goethite and limonite with carbonaceous shale. Such deposits are generally thin and small. 18. Environmental geology. Ironstone deposits typically consist of goethite and hematite ores without chert and are generally formed in shallow marine and deltaic environments. However, the origin of ironstones is complex and many models have been given by number of workers. One of the most important source of iron is the banded iron formation. Banded iron formation (BIF) is characterized by its fine layering of 0.53 cm thick. The layering consists of silica layers, in the form of chert or better crystallized silica, alternating with layers of iron minerals, mostly hematite and magnetite. An extraordinary fact emerging from recent studies is that the great bulk of iron formations of the world was laid down in the very short time interval of 2500–1900 Ma ago. Four important facies, represented by oxide, carbonate, silicate and sulfide facies are commonly associated with BIF. Other deposits formed by such process are the bedded manganese oxide ores, phosphorites, evaporites, carbonaceous, black shales, and manganese nodules. 5.2.2 Residual concentration. In contrast to the deposits considered in the previous section, where the concentration into ore bodies of sedimentary material is removed by mechanical or chemical processes and redeposited elsewhere, sometimes the material left behind has been sufficiently concentrated by weathering processes and groundwater action to form residual or deposits. The chemical weathering processes are the dominantly responsible for the formation of residual concentration deposits. These includes the processes by which rocks that are near surface tends to achieve equilibrium with the surface environment. According to Leader, 1999, the main chemical processes that contribute to weathering include dissolution, oxidation, hydrolysis, and acid hydrolysis. From orogenetic aspects, chemical weathering can be subdivided into three processes: a, dissolution of rock material and the transport, removal of soluble ions and molecules by aqueous solutions; b, production of new minerals, in particular clays, oxides and hydroxides, and carbonates; and c, accumulation of unaltered, low solubility residual materials such as silica, alumina, and gold. For the formation of extensive deposits, intense chemical weathering, such as in tropical climates having a high rainfall, is necessary. In such situations, most rocks yield a soil from which all soluble material has been dissolved, and these soils are called laterites. As iron and aluminium hydroxides are amongst the most insoluble of natural substances, laterites are composed mainly of these materials and are, therefore, of no value as a source of either metal. Sometimes, however, residual deposits can be high-grade deposits of one metal only. The relative solubilities of different elements in surface waters depends on a variety of factors like A, pH, ionic potential, cation exchange, oxidation, hydrolysis, etc. It can, however, be qualitatively predicted in terms of their ionic potential, plural see figure 4.1 from page 221 of the book by Robb, 2005. Cations with low ionic potentials, less than 3, are easily hydrated and are mobile under a range of conditions, although they will precipitate under alkaline conditions and are readily absorbed by clay particles. Similarly, anions with high ionic potentials, greater than 10, form soluble complexes and dissolve easily, but will precipitate together with alkali elements. Ions with intermediate. 19. Environmental geology. Values ionic potentials between 3 and 10 tend to be relatively insoluble and precipitate readily as hydroxides. Silicon is more soluble than Al in the pH range at which most groundwaters exist, 5 to 9. Therefore, during the chemical weathering, leaching of C from the rock takes place, which leads to residual concentration of immobile Al and ferric oxides, hydroxides. This is typical of soil formation processes in tropical, high rainfall areas and yields lateritic soil profiles which can also contain concentrations of bauxite, aluminum ore, and Ni. Lateritic soils will not, however, form under acidic conditions, pH less than 5, as Al is more soluble than C. Based on the concentration of iron and/or aluminum, Al, Fe ratio, the laterites are subdivided into a bauxite Sp, alumino-ferruginous laterite, and C, ferruginous laterites, commonly called as laterite. Ore-grade bauxite generally contains more than 50% Al2O3. The other laterites are important when they contain some valuable metals in sufficient concentration, e.g. Nalaterites, olaterites, etc. The conditions required for the formation of residual concentration deposit by weathering processes are: a parent rock of appropriate composition, b. desired conditions for leaching of the undesirable constituents by intense chemical weathering and adequate water supply, c. low relief, and d. tectonic stability of the region. The bauxite, which is the principal source of aluminum metal, is composed of 3 alhydroxide minerals gibbsite, boehmite, and diaspore in different proportions. It is typically formed from this process. The residual concentration of aluminum-rich material in the upper zone of the lateritic profile is a function of higher rainfall, lower average temperature, around 220 C, higher humidity, and near neutral pH conditions, between 4.5 to 9. The other precondition is the presence of alumina-rich minerals in the rock, effective rock porosity to allow free circulation of water, low to moderate topographical relief, and prolonged crustal stability. The alumina-rich minerals like feldspar and kaolinite participate in the incongruent dissolution resulting in the leaching of C. The holding of Al in the residue give rise to gibbsite and other alumina hydroxide minerals. The process can be represented as feldspar, loss of C, right pointing arrow kaolinite, loss of C, right pointing arrow gibbsite, Al-O3. The bauxite deposits of eastern coast and Amarkantak, etc. are typical examples from India. The other important deposit formed from this process is the Ni laterites. It is interesting to note that the first major nickel production in the world came from nickelifers laterites in New Caledonia, where mining commenced in about 1876. Residual nickel deposits are formed by the intense tropical weathering of ultramafic rocks rich in trace amounts of nickel, such as periddotites and serpentinites. The ore formation process of Ni laterite is simple and involved temporarily passing of Ni into solution from the uppermost lateritic residuum and quickly getting reprecipitated, concentrated in underlying saprolitic layer either as smectite or as garnierite and other nickeliferous phyllosilicates, and less commonly. 20. Environmental geology. With goethite in the weathered rock below the laterite. A typical environment of the Ni laterite formation is given in Fig 6, Figs 19.2 and 19.3 from the Book of Evans, 2009. Fig 6. Development of a residual nickeliferous laterite deposit, Fig 19.2 and Fig 19.3 from Book of Evans, 1993. 5.2.3 Supergene enrichment process. The other important process caused by the chemical weathering is responsible for the in situ enrichment of the metal in the pre-existing primary or hypogene sulfide body. This process is known as supergene enrichment. Oxidation and hydrolysis of the sulfide minerals in the upper portion of the weathering profiles is an integrated part of this process. The metals are first released from the unstable sulfide minerals and then percolate down along with the meteoric water and reprecipitate as oxides and sulfide mineral phases in the subsurface environment. A typical profile of a supergene enriched mineral deposit consists of 3 zones from bottom to top: a hypogene or protor zone, B, supergene enrichment zone, and C, oxidized zone, Figure 7. A cap rock or gossan may be present on the top of the oxidized zone. The oxidized zone generally lie above the water table. The surface water, while percolating down the low-grade sulfide ore bodies, oxidize many ore minerals which are unstable under oxidizing conditions, resulting into the leaching of. 21. Environmental geology. Metals is soluble sulfate solution. Some of the metals got precipitated as hydroxides and carbonate minerals which are stable under oxidizing conditions like malachite and azurite. The chemical reactions can be given for various situations. However, since the pyrite is one of the most commonest ore minerals present in sulfide deposits, it get oxidized to give the strong oxidizing solvents, e.g. H2SO4 and Fe2, SO4, 3. The reactions can be written as. This acts as a geological guide for the search of sulfide deposit. A characteristic product of the oxidized zone is limonite. The ferric hydroxide is left behind. 2. The ferric hydroxide is left behind to form a residual deposit at the surface, and this is known as a gossan or iron hat. This acts as a geological guide for the search of sulfide deposit. A characteristic product of the oxidized zone is limonite. It may be formed either by hydrolyzation of ferric sulfate or by direct oxidation of pyrite, may be represented by following reaction. Fe2, so 4 Fes. So when the percolating solution with bulk of the dissolved metals reaches the water table, it again precipitates as sulfide, enriching the grade of protor. This zone hence is known as enriched zone or zone of supergene enrichment. Typical reactions in this zone may be represented as PbS plus CuSO4 equals Cus plus PbSO4, galena, cobalt, angelicite. Fig 7. Schematic cross-section of a sulfide-bearing bean showing relationship between zone of oxidation, supergene enrichment, and hypogene sulfide, after Jensen and Bateman, 1979, source Fig 2.17 from book by K.C. Mishra, 2009. Fes plus 1,4 CuSO, 4 plus 12 H2O equals 7 C.